Hello students, in today's class we shall discuss the elevation of boiling point. So in previous classes we have studied that the vapor pressure of pure solvent is always greater than the vapor pressure of the solution, because if the solution is having one of the component, that is, if the solute is non-volatile in nature, so it reduces the escaping tendency of the solute particles into the vapor phase. Hence, the vapor pressure of solution is always lesser compared to pure solvent. So in this elevation of boiling point, the vapor pressure of liquid increases with increase in temperature. See here, so if you consider this point, the temperature is less. So as the temperature has increased to this point, the vapor pressure also increased. Even it is same for solution. Here the temperature will be less. As the temperature increases, so the vapor pressure also increases. So this diagram, it depicts the variation of vapor pressure of pure solvent and that of the solution of a non-volatile solute dissolved in it as a function of temperature. So here this solution, it consists of a non-volatile solute and the solvent. So this is the vapor pressure of pure solvent. The vapor pressure of a solution of a non-volatile solute in volatile solvent is always lower than that of the pure solvent. So further, a liquid boils at a temperature when its vapor pressure is equal, or it becomes equal to the atmospheric pressure. So that point is called as boiling point. Whenever the vapor pressure of the solvent or solution, when it becomes equal to the atmospheric pressure, so this point, at this point we will say that it is the boiling point of pure solvent and this is the boiling point of solution. If we compare the boiling point of solvent as well as solution, so this solution is having higher boiling point than the pure solvent because it consists of non-volatile solute. Since it contains non-volatile solute, it requires more temperature for the boiling. Hence, the boiling point of solution is always greater than the boiling point of solvent. Let T0 B be the boiling point of this pure solvent and TB be that of the solution. The increase in boiling point, that is given by delta TB. So this delta TB, so this can be determined by TB minus TB naught. That means that the boiling point of pure solvent and boiling point of solution. So TB, that is the boiling point of solution minus boiling point of solvent, that will give you the boiling point elevation. This delta TB, this is equal to TB minus TB naught. It is also known as elevation of boiling point. So this term is called as elevation of boiling point. Experiments have shown that for dilute solutions, the elevation of boiling point, that is delta TB, is directly proportional to molar concentration of the solution. So delta TB, it is directly proportional to molar concentration. Now if I write delta TB, if I remove this proportionality constant, I need to introduce some constants. So I will take KB yum, where yum, small letter yum, this is the molarity of the solution. And KB, this is known as boiling point elevation constant or molar elevation constant, or even it is called as ebuloscopic constant. Now, if molarity of that solution is equal to unity, now if yum is equal to 1, then delta TB will be equal to boiling point elevation constant, that is KB. So now we can define this KB value. So KB, it is known as the boiling point elevation constant. So molar elevation constant of a solution is defined as the elevation of boiling point delta TB caused by dissolving 1 mole of non-volatile solute in 1000 gram of solvent. So the definition is here. Molar elevation constant is Kb of a solvent is defined as the elevation of boiling point caused by dissolving 1 mole of non-volatile solute in 1000 gram of the solvent. So here we have taken 1000 gram because it is a molar constant. So if you want to define molarity, we will use 1000 gram or per kg. So hence this non-volatile solute is dissolved in 1000 gram or 1 kg of the solvent. Now let us come to the unit of Kb, molar elevation constant. It is Kelvin per molar. So molar solution, that is nothing but mole per kg. So hence we can also write it as mole. So Kelvin mole per kg, or the best way is Kelvin kg per mole. So now if you remove this bracket, so now if you remove this bracket, so this becomes Kelvin per kg per mole. So this per kg, this minus 1, so that will cancel. So hence we are going to get kg, and this is mole, that is expressed in the parenthesis of per. So it becomes per mole. So Kelvin kg per mole. Now let me consider two components, that is component A as solvent and component B as solute. Now if WB gram of solute having MB, that is molar mass of MB, is dissolved in WA gram of solvent. So mass in gram of the solvent, that is number of moles of solute. Now we can write this molarity of the solution. So the molarity of the solution, that is equal to 1000 by mass of the solvent, that is Wa, into mass of solute and molar mass of the solute. So why we have taken 1000 here? Because the solute is dissolved in 1 kg of the solvent. Now delta TB, what we know is delta TB. So this is equal to Kb into molarity. Now in place of M, if I substitute the molarity value, so this becomes Kb into 1000 into Wb, that is mass of solute, divided by mass of solvent into molar mass of solute. This is delta TB value. So what I will do is I will rearrange the terms, that is delta TB is equal to 1000 into Kb into Wb whole divided by Wa into Mb, molar mass of solute. Now if I want to determine the molar mass of solute, then Mb is equal to 1000 into Kb into Wb whole divided by Wa into delta Tb. So from this equation we can determine the molar mass of solute. In order to determine the molar mass of non-volatile solute, that is Mb, a known mass of, that is Wb, mass of solute, is dissolved in known mass of the solvent, that is Wa, whose Kb value, so this Kb value is known. The elevation of boiling point delta Tb is determined experimentally. So here are the values of some solvents. So boiling point, it is expressed in Kelvin. This molar elevation point, molar boiling point elevation constant, that is expressed in Kelvin kg per mole. So for water, so it boils at 100 degrees Celsius, so that is expressed in Kelvin, that is 373.15, and its Kb value is 0.52. Ethanol, it is 351.5 is the boiling point, and 1.20 is the molar boiling point elevation constant. For cyclohexane, the boiling point is 353.74 and Kb value, that is 2.79. For benzene, 353.3 and 2.53. For chloroform, it is 334.4 and Kb value is 3.63. For carbon tetrachloride, boiling point is 350 and Kb value is 5.03. And for carbon disulfide, its boiling point is 319.4 and Kb value is 2.34. Thank you.